far beyond Earth, in the cold outer regions of our solar system, Saturn is surrounded by dozens of moons. Most of them are silent, frozen worlds, ancient bodies locked in ice and darkness. But one of these moons is different. Its name is Enceladus. At first glance, Enceladus looks small and quiet. It is only about 500 kilometers wide, smaller than many countries on Earth. Its surface is covered in bright ice, reflecting sunlight so strongly that it is one of the most reflective objects in the entire solar system. For a long time, scientists believed it was nothing more than a frozen ball of ice. But then, something extraordinary was discovered from cracks near its south pole. Enceladus is shooting gigantic plumes of water vapor, ice particles, and organic molecules hundreds of kilometers into space. These eruptions are so powerful that they feed Saturn's enormous E-ring, continuously spraying material into orbit around the planet. In other words, Enceladus is not a dead world. It is geologically active. Something beneath its icy surface is heating the moon from within, forcing water from a hidden ocean to burst through giant fractures in the crust and escape into space like cosmic geysers. This discovery completely changed how scientists think about where life might exist in the solar system. Because beneath that frozen shell, Enceladus may contain a vast global ocean of liquid water. And where there is liquid water, there is the possibility of life. In this video, we will explore one of the most extraordinary worlds ever discovered, the icy moon that is literally erupting into space, a tiny world orbiting Saturn that may hold one of the best chances of finding alien life beyond Earth. Enceladus was not always considered one of the most important worlds in the solar system. For most of the history of astronomy, it was simply another small moon orbiting Saturn, one of dozens of icy bodies moving quietly through the darkness. When it was first discovered in 1789 by the astronomer William Herschel, it appeared as nothing more than a faint point of light through a telescope. At that time, there was no way to know what this distant moon actually looked like, let alone what secrets might be hidden beneath its surface. For more than 2 centuries, Enceladus remained mysterious and largely ignored. Compared to Saturn's largest moon, Titan, which has a thick atmosphere and vast lakes of liquid methane, Enceladus seemed insignificant. It was tiny, only about 504 kilometers in diameter. That makes it smaller than many countries on Earth. In fact, if you placed Enceladus on our planet, it would barely stretch across a large continent. Because of its small size, scientists originally believed that Enceladus should be completely frozen and geologically dead. Small worlds lose heat quickly. Without internal heat, there is no energy to drive geological activity, no volcanoes, no tectonic movement, no atmosphere, nothing but an ancient frozen surface that has remained unchanged for billions of years. That assumption seemed reasonable for a long time. But as technology improved and spacecraft began exploring the outer solar system, the story of Enceladus slowly began to change. The first real close look came in the early 1980s when NASA's Voyager spacecraft flew past Saturn. Voyager 1 and Voyager 2 captured the first detailed images of the moon. What scientists saw immediately raised questions. Instead of being covered in ancient impact craters like most icy moons, Enceladus appeared unusually smooth and bright. Its surface reflected almost all the sunlight that struck it. In fact, Enceladus reflects about 99% of the sunlight it receives, making it the most reflective known body in the solar system. This brightness was unusual because surfaces in space gradually darken over time. Micrometeorites constantly bombard moons and planets, leaving behind dust and debris that slowly build up over millions or billions of years. A very bright surface usually means something is constantly renewing it, covering old terrain with fresh material. But how could such a small moon still be active? Voyager images showed something else that puzzled scientists. Enceladus did not have a uniform surface. Instead, it displayed a strange mixture of landscapes. Some regions were heavily cratered, suggesting ancient terrain that had not changed for billions of years. Other regions were incredibly smooth and almost completely free of craters. This indicated that parts of the moon were much younger than others. Somehow, Enceladus had experienced geological activity in the past, activity strong enough to erase craters and reshape its surface. But where had the energy come from? And could it still be happening today? At the time, scientists could not answer these questions. The Voyager flybys lasted only a short time, and the spacecraft could not stay to study the moon in detail. After Voyager left Saturn behind, Enceladus returned to being a distant mystery. For the next 2 decades, astronomers could only speculate. Some scientists proposed that Enceladus might contain pockets of liquid water beneath its frozen crust. Others suggested that the moon might once have been heated by radioactive elements inside its core. But these ideas were difficult to confirm without a dedicated spacecraft studying the Saturn system for long periods of time. That opportunity finally arrived in 2004 when NASA's Cassini spacecraft entered orbit around Saturn. Cassini was one of the most ambitious planetary missions ever launched. Unlike previous spacecraft that simply flew past planets, Cassini was designed to remain in orbit around Saturn for years, carefully studying the planet, its rings, and its many moons. Almost immediately, Enceladus became one of Cassini's most surprising discoveries. During early observations, Cassini noticed something strange near the moon's south pole. Instruments detected faint clouds of tiny particles surrounding the moon. At first, scientists were unsure what they were seeing, but as Cassini made closer passes, the evidence became undeniable. Enceladus was not just geologically active, it was erupting. From deep cracks in the moon's icy surface, enormous plumes of water vapor and ice particles were blasting out into space. These geysers were powerful enough to shoot material hundreds of kilometers above the moon's surface. It was one of the most astonishing discoveries in planetary science. Until that moment, scientists had only seen this kind of activity on Earth and a few other large worlds. No one expected such a small icy moon to be capable of producing massive eruptions. Even more surprising was what those plumes contained. Cassini's instruments detected not just water ice, but also organic molecules, carbon dioxide, methane, ammonia, and tiny grains of salt-rich material. These chemicals strongly suggested that the material was coming from a liquid ocean hidden beneath the moon's frozen crust. In other words, Enceladus was not just erupting ice. It was venting material from an underground ocean. The cracks where these plumes erupted became known as the tiger stripes. These enormous fractures stretch across the south polar region of the Moon. Each one is hundreds of kilometers long and several kilometers deep. Thermal sensors aboard Cassini revealed that these fractures were much warmer than the surrounding surface. While most of Enceladus is extremely cold, around -200 degrees Celsius, the tiger stripe regions were significantly warmer, indicating heat rising from below. Something inside Enceladus was generating energy. But how? One of the most important clues came from the Moon's orbit around Saturn. Enceladus does not orbit the planet in a perfect circle. Instead, its orbit is slightly elliptical, meaning the distance between the Moon and Saturn constantly changes. As Enceladus moves closer and farther away from Saturn, the planet's immense gravity stretches and squeezes the Moon slightly. This process is called tidal heating. Every time Enceladus completes an orbit, Saturn's gravity flexes the Moon's interior. This constant stretching generates friction and heat deep within the Moon's core. It is similar to bending a metal wire repeatedly. The more you bend it, the warmer it becomes. Inside Enceladus, this tidal heating appears to be strong enough to melt ice beneath the surface, creating a vast subsurface ocean. Cassini's measurements eventually confirmed that this ocean likely exists beneath most of the Moon's icy crust. The ocean may be tens of kilometers deep and could extend around the entire globe beneath the ice shell. But what makes Enceladus truly extraordinary is not just the existence of this ocean. It is the fact that the ocean is connected directly to space. Through the tiger stripe fractures, material from the ocean is constantly escaping into space in the form of geysers. This means that scientists do not need to drill through kilometers of ice to study the ocean. Instead, spacecraft can simply fly through the plumes and analyze the material directly. Cassini did exactly that. During several daring flybys, the spacecraft passed directly through the erupting plumes, collecting particles and analyzing their composition. The results were astonishing. In addition to water and organic molecules, Cassini detected tiny grains of silica. These particles form when hot water interacts with rocky material at high temperatures. On Earth, this process occurs near hydrothermal vents on the ocean floor. Hydrothermal vents are environments where superheated water rises from deep within the planet's crust. These vents are rich in minerals and chemicals, and they provide energy that can support entire ecosystems. Some of the most extreme life forms on Earth live around hydrothermal vents, surviving without sunlight and relying entirely on chemical energy. The discovery of silica particles strongly suggested that similar hydrothermal activity might exist on the ocean floor of Enceladus. If that is true, then the Moon may have three key ingredients required for life: liquid water, chemical nutrients, and a source of energy. These conditions make Enceladus one of the most promising places in the solar system to search for extraterrestrial life. Even though it is small and distant, this icy moon may contain an environment surprisingly similar to the deep oceans of Earth. Today, scientists consider Enceladus one of the most important targets for future exploration. Future missions may one day send advanced spacecraft back to Saturn, specifically to study this moon in greater detail. Some mission concepts even propose sending probes capable of flying repeatedly through the plumes to search for complex organic molecules or even microscopic life. For now, however, Enceladus remains a tantalizing mystery, a small moon hidden in the cold outer reaches of the solar system, quietly erupting enormous plumes of ocean water into space. A frozen world that should have been dead billions of years ago, yet somehow remains alive with activity, and beneath its bright icy surface, an ocean may be waiting, holding secrets that could transform our understanding of life in the universe. Enceladus may appear small and fragile compared to the giant planets and massive moons of the solar system, but its interior is far more complex than scientists once imagined. Beneath the moon's brilliant icy surface lies a hidden structure that is constantly changing under the influence of powerful gravitational forces. To understand why Enceladus is erupting into space, we first need to explore what the inside of this mysterious moon might look like. At the very center of Enceladus is believed to be a rocky core. Unlike the icy outer layers, this core is composed of silicate rock, similar to the materials that make up Earth's crust and mantle. Based on measurements of the moon's density and gravitational field, scientists estimate that this rocky interior makes up most of the moon's total mass. Surrounding this core lies one of the most extraordinary features ever discovered beyond Earth: a global ocean of liquid water. For many years, the idea of a liquid ocean inside Enceladus seemed almost impossible. The moon is extremely far from the sun, orbiting Saturn nearly 1.4 billion kilometers away from Earth. At this distance, sunlight is incredibly weak. The surface temperature of Enceladus is around minus 200 degrees Celsius, cold enough to freeze almost anything solid. Yet despite these extreme temperatures, the interior of the moon remains warm enough for liquid water to exist. The reason for this paradox lies in the powerful gravitational relationship between Enceladus and Saturn. Saturn is an enormous planet, more than 95 times the mass of Earth. Its gravitational pull is so strong that it constantly stretches and squeezes the smaller moons orbiting around it. Because Enceladus does not travel in a perfectly circular orbit, the strength of Saturn's gravity changes slightly as the moon moves closer and farther away from the planet. This creates a rhythmic cycle of compression and expansion inside the moon. Every orbit around Saturn causes Enceladus to flex like a rubber ball, being squeezed repeatedly. These tidal forces generate friction inside the moon's interior, producing heat deep beneath the surface. This process is known as tidal heating, and it is one of the most important sources of energy in the outer solar system. Without tidal heating, Enceladus would have frozen solid billions of years ago. But with Saturn constantly pulling and stretching it, the moon's interior remains active and dynamic. Over time, this heat gradually melts portions of the icy interior, forming an enormous subsurface ocean between the rocky core and the frozen outer shell. Scientists estimate that the ice crust covering this ocean may be between 20 and 30 kilometers thick in most regions. However, near the South Pole, where the famous geysers erupt, the ice shell appears to be much thinner. In some areas around the tiger stripes, the crust may be only a few kilometers thick. This thinner ice allows heat from the interior to escape more easily, creating weak points where water and vapor can break through to the surface. These fractures act like enormous pressure valves for the hidden ocean below. As the ocean water warms and pressure builds beneath the ice shell, it begins to force its way upward through these cracks. When the water reaches the near vacuum of space, it rapidly expands and freezes into tiny ice particles. This is what creates the spectacular plumes observed by the Cassini spacecraft. Each plume contains a mixture of water vapor, microscopic ice grains, and various dissolved chemicals that originated from the ocean below. The eruptions occur continuously, although their intensity changes slightly depending on where Enceladus is in its orbit. Interestingly, the plumes become strongest when the Moon is farthest from Saturn. At this point in its orbit, the tidal stresses pulling on the crust cause the tiger stripe fractures to widen slightly. This allows more material from the ocean to escape into space. When Enceladus moves closer to Saturn, the gravitational pressure increases again, compressing the fractures and partially closing them. This rhythmic opening and closing of the cracks acts almost like the breathing of the Moon itself. The water escaping from Enceladus does not simply disappear into space. Much of the material becomes trapped in orbit around Saturn, forming a vast, diffuse structure known as the E-ring. Saturn's E-ring is one of the largest rings in the solar system, stretching hundreds of thousands of kilometers outward from the planet. Unlike the bright main rings of Saturn, which are composed of large chunks of ice, the E-ring consists mainly of extremely fine particles. Scientists now believe that Enceladus is the primary source of this ring. Every second, the Moon ejects hundreds of kilograms of water vapor and ice into space. Over time, this material spreads outward, replenishing the particles that make up the E-ring. Without the constant activity of Enceladus, the E-ring would gradually disappear as its particles drift away or are pulled into Saturn's atmosphere. In this way, Enceladus is not just a moon of Saturn. It is actively shaping the entire Saturn system. The plumes erupting from its surface have another remarkable consequence. Because they extend so far into space, they create a massive cloud of gas and ice around the Moon itself. This cloud interacts with Saturn's powerful magnetic field, creating complex electrical and plasma phenomena. Cassini detected strong interactions between the particles from Enceladus and the magnetosphere of Saturn. Charged particles in the plumes become trapped by magnetic forces, forming a dynamic environment of plasma and energetic particles surrounding the Moon. These interactions further demonstrate just how active Enceladus truly is. But perhaps the most exciting discovery came from analyzing the chemical composition of the plume material. Cassini's instruments detected simple organic molecules, carbon-based compounds that are considered essential building blocks for life. These included methane, carbon dioxide, and other complex chemicals that could potentially support biological processes. Even more intriguing was the presence of molecular hydrogen in the plume gases. Hydrogen is particularly important because it can serve as a source of chemical energy for microbial life. On Earth, many deep-sea organisms survive by using hydrogen produced by hydrothermal vents at the ocean floor. When scientists realized that hydrogen was present in the plumes of Enceladus, it suggested that similar hydrothermal reactions might be occurring inside the Moon. If hot water from the interior is interacting with the rocky core, it could create environments similar to Earth's hydrothermal vent systems, environments that are known to support thriving ecosystems. This discovery dramatically increased the scientific interest in Enceladus. For decades, scientists believed that the most promising place to search for life beyond Earth was Mars. But Enceladus has now joined a short list of worlds where the conditions may be suitable for life. In fact, some researchers believe that Enceladus might even be a better candidate than Mars for discovering extraterrestrial organisms. Mars was once warm and wet billions of years ago, but its surface is now cold and dry. Any life that might exist there today would likely be buried deep underground. Enceladus, on the other hand, still contains an active ocean today, and that ocean is constantly venting material into space where it can be studied directly. This makes the Moon uniquely accessible for future exploration. A spacecraft does not need to land on the surface or drill through the ice to study the ocean. Instead, it can simply fly through the plumes and collect samples. This possibility has inspired several proposed missions designed specifically to investigate Enceladus more closely. Some mission concepts involve sending orbiters that repeatedly pass through the plumes, analyzing their chemistry in extreme detail. Other ideas propose landing spacecraft near the tiger stripe fractures to study the surface directly. One of the most ambitious proposals even involves sending a probe capable of descending through the ice crust into the ocean itself. Such a mission would be incredibly difficult, but the scientific rewards could be extraordinary. If life exists anywhere beyond Earth within our solar system, Enceladus may be one of the best places to find it. For now, however, the Moon continues to erupt quietly around Saturn, sending streams of icy particles into the darkness of space. A tiny world with a hidden ocean beneath its frozen surface, constantly revealing small pieces of its secret interior with every plume that bursts into the vacuum above. The eruptions on Enceladus are not random. They come from a specific region of the Moon, a mysterious area near the South Pole that completely changed how scientists view icy worlds. This region is unlike anything else seen on the Moon, or even anywhere else in the solar system. Stretching across the southern hemisphere are 4 enormous fractures in the ice crust. These cracks are hundreds of kilometers long and several kilometers wide. When scientists first observed them in Cassini images, they immediately stood out because of their dark coloration compared to the surrounding bright ice. Because of their striped appearance, researchers nicknamed them the tiger stripes. These fractures are officially named Alexandria sulcus, Cairo sulcus, Baghdad sulcus, and Damascus sulcus. Each one runs roughly parallel to the others across the Moon's south polar terrain. They cut deep into the icy crust like scars carved across the surface. But these are not ordinary cracks. They are the source of the Moon's incredible geysers. Cassini observations revealed that the plumes erupt directly from these fractures. Thousands of individual jets spray material upward from small vents along the tiger stripes, forming massive curtains of vapor and ice particles that rise high above the Moon's surface. Some of these plumes reach hundreds of kilometers into space. If you were standing on the surface of Enceladus near one of these fractures, the sight would be extraordinary. Towering geysers of water vapor would blast upward into the black sky, expanding rapidly as they escaped into the near vacuum above the moon. But the most surprising thing about the tiger stripes is not just the eruptions themselves, it is the heat. When Cassini scanned the region using its infrared instruments, scientists expected to see extremely cold temperatures similar to the rest of the moon's frozen surface. Instead, they detected something shocking. The tiger stripes were much warmer than the surrounding terrain. While most of Enceladus is colder than -200 degrees Celsius, the fractures themselves were tens of degrees warmer. This may not sound like much by Earth standards, but for such a small icy moon, it was a massive difference. It meant that heat was rising from deep inside the moon. This discovery provided crucial evidence that Enceladus was still geologically active. Scientists soon realized that the tiger stripes were acting as enormous vents, allowing internal heat and material from the subsurface ocean to escape into space. The cracks likely extend deep through the ice shell, connecting the surface directly to the ocean beneath. However, one major question remained. Why was the activity concentrated at the South Pole? Most moons and planets with internal heat tend to distribute that energy across their entire surface. But on Enceladus, the activity seemed to be focused in a single region. Researchers began studying the moon's internal structure more carefully, searching for clues. One explanation involves the thickness of the ice shell. Measurements suggest that the ice crust beneath the South Pole is thinner than elsewhere on the moon. If the crust is thinner, heat from the interior can escape more easily through that region. Over time, this could create a feedback loop where the warmer area becomes even thinner and more active. As heat melts ice beneath the crust, liquid water may accumulate beneath the fractures. Pressure builds as tidal forces from Saturn squeeze the moon's interior. Eventually, the pressurized water finds its way through the cracks and erupts into space. But there may be an even deeper reason for the unusual location of the tiger stripes. Enceladus is locked in a complex gravitational relationship with several of Saturn's other moons. One of the most important of these interactions involves the moon Diana. Dione is larger than Enceladus and orbits Saturn slightly farther away. The two moons are locked in what astronomers call an orbital resonance. For every 2 orbits that Enceladus completes around Saturn, Dione completes exactly 1. This resonance keeps Enceladus's orbit slightly elliptical rather than perfectly circular. Without this gravitational interaction, the moon's orbit would eventually become more stable and circular over time. But because of Dione's influence, the orbit remains slightly stretched. That stretched orbit is critical. It ensures that Saturn's tidal forces continue flexing the moon's interior, constantly generating heat. Without this ongoing tidal heating, the ocean beneath Enceladus would likely freeze solid over millions of years. In a way, Dione is indirectly responsible for keeping Enceladus alive. The combined gravitational pull of Saturn and Dione creates the conditions necessary for the moon's ongoing activity. Another mystery surrounding the tiger stripes is their remarkable stability. Despite the constant eruptions and stresses placed on the crust, the fractures appear to remain open over long periods of time. Scientists once worried that the cracks would quickly freeze shut, stopping the geysers. But observations show that the vents have been active for many years. One explanation is that the constant movement of water through the fractures prevents them from sealing closed. Warm water rising from the ocean may melt the surrounding ice slightly, keeping the cracks open and allowing the eruptions to continue. In this sense, the plumes themselves may help sustain the activity. The tiger stripes also show signs of geological youth. The terrain around them is relatively smooth and free of large impact craters. This suggests that the region has been resurfaced recently, perhaps within the last few million years. In planetary terms, that is extremely recent. It means that Enceladus is not just an ancient world that once experienced activity in the distant past. It is active today. Some researchers even believe that the Moon's activity may have intensified over time as tidal heating gradually increased. The South Polar terrain shows evidence of complex tectonic patterns. Ridges, valleys, and fractures crisscross the region, suggesting that the ice shell has been repeatedly stretched, cracked, and reshaped by internal forces. The surface around the tiger stripes is also covered in fine ice particles that have fallen back down from the plumes. When the geysers erupt, not all of the material escapes into space. Some of the particles follow curved trajectories and fall back onto the Moon's surface like snow. Over time, this process gradually blankets the surrounding terrain with fresh ice, helping maintain the Moon's incredibly bright appearance. This constant resurfacing explains why Enceladus remains the most reflective object in the solar system. It is literally coating itself with fresh ice. As scientists continued studying the plumes, they began noticing something else fascinating. The eruptions were not completely constant. Instead, their strength changed depending on where Enceladus was in its orbit around Saturn. When the Moon was farther from Saturn, the fractures opened slightly wider due to tidal stress, allowing more material to escape. When the Moon moved closer to Saturn, the cracks compressed slightly and the plume activity decreased. This meant that the Moon's geysers were directly controlled by Saturn's gravity. Every orbit around the planet caused the Moon's crust to flex and breathe. This discovery provided some of the strongest evidence that tidal heating was driving the activity beneath the surface. But the more scientists studied Enceladus, the more complex the story became. Computer simulations suggested that the heat produced by tidal forces might not be enough on its own to explain the enormous energy needed to power the plumes. Some researchers began proposing additional mechanisms. One possibility is that the rocky core of Enceladus may be more porous than originally thought. If the core contains cracks and cavities filled with water, tidal flexing could generate heat through friction as the water flows through the rock. This process could dramatically increase the amount of heat produced inside the Moon. Another idea involves chemical reactions between water and the minerals in the core. When certain minerals interact with hot water, they release energy through a process known as serpentinization. This reaction also produces hydrogen gas, the same hydrogen detected in the plumes by Cassini. If serpentinization is occurring inside Enceladus, it could provide both heat and chemical energy for potential life. All of these discoveries have transformed Enceladus from an obscure icy moon into one of the most scientifically important worlds in the solar system. The tiger stripes are not just geological curiosities. They are windows into an ocean hidden beneath kilometers of ice. Every plume that erupts from those fractures carries tiny pieces of that ocean into space, fragments of a hidden environment that may contain the ingredients for life. And with every new observation, Enceladus continues to reveal more about the mysterious processes shaping icy worlds far from the warmth of the sun. For centuries, humans believed that life could only exist in environments similar to Earth's surface, places with sunlight, moderate temperatures, and stable climates. The idea that life might survive in the frozen darkness of the outer solar system seemed almost impossible. But Enceladus forced scientists to reconsider everything they thought they knew about where life could exist. The discovery of an underground ocean beneath the icy crust of Enceladus immediately raised one profound question. Could that ocean be habitable? To answer that question, scientists began comparing Enceladus to environments on Earth where life thrives in extreme conditions. One of the most important discoveries in Earth's oceans came in the late 1970s when researchers first explored hydrothermal vents on the deep sea floor. These vents exist along cracks in Earth's crust, where seawater seeps down into the planet's interior, becomes superheated by magma, and then rises back toward the surface, carrying dissolved minerals and chemicals. The conditions around these vents are extreme. Temperatures can exceed 400 degrees Celsius. The pressure is immense, and sunlight never reaches these depths. For a long time, scientists assumed that such environments would be completely lifeless. But when robotic submarines first explored these deep ocean vents, they discovered thriving ecosystems. Entire communities of organisms were living around the vents. Giant tube worms, shrimp, bacteria, and many other species were feeding on chemical energy produced by the vents rather than sunlight. This discovery fundamentally changed our understanding of life. It showed that life does not necessarily require sunlight. Instead, it can survive by using chemical reactions as an energy source, a process known as chemosynthesis. When scientists began studying the plumes of Enceladus, they realized that similar conditions might exist inside the moon's hidden ocean. Cassini's instruments detected several key ingredients that are considered essential for life. First, there is liquid water. Water is the universal solvent for biological chemistry. Every known living organism on Earth depends on water for its metabolic processes. The existence of a large subsurface ocean immediately makes Enceladus far more interesting from a biological perspective. Second, there are organic molecules. Cassini detected simple carbon-based compounds within the plumes, erupting from the tiger stripes. Organic molecules are the building blocks of life. While their presence does not prove that life exists, it shows that the raw materials for life are present. Third, there is chemical energy. The detection of molecular hydrogen within the plumes was one of the most important discoveries of the Cassini mission. Hydrogen gas can be produced when hot water interacts with certain minerals inside rocky environments. On Earth, microorganisms living near hydrothermal vents often rely on hydrogen as an energy source. They combine hydrogen with carbon dioxide in chemical reactions that produce energy and organic compounds. The fact that hydrogen exists in the plumes of Enceladus strongly suggests that similar chemical reactions may be occurring deep inside the moon. And finally, there are nutrients. Cassini detected salts and silica particles in the plume material. These substances likely originated from interactions between ocean water and the rocky core beneath the ice shell. This interaction is important because it allows minerals and nutrients to dissolve into the ocean, providing the chemical ingredients necessary for biological processes. Taken together, these discoveries suggest that Enceladus may contain a surprisingly Earth-like environment beneath its frozen surface, an ocean of liquid water, chemical nutrients, sources of energy, and organic molecules. In many ways, these are the same conditions that allowed life to emerge on Earth billions of years ago. Of course, this does not mean that life actually exists on Enceladus, but it means that the moon possesses many of the ingredients that scientists believe are necessary for life to develop. Some researchers believe that microbial organisms could potentially survive in Enceladus's ocean, especially near hydrothermal vents on the seafloor. If life does exist there, it would likely be microscopic, similar to bacteria or archaea found in Earth's deep oceans. These organisms would probably rely entirely on chemical energy rather than sunlight. But even the discovery of simple microbial life beyond Earth would be one of the most important scientific discoveries in human history. It would show that life is not unique to our planet, and it would suggest that the universe may be filled with living worlds waiting to be discovered. The possibility of life on Enceladus has inspired scientists to begin planning future missions specifically designed to search for biological signatures. Several mission concepts have been proposed over the past decade. One idea involves sending an advanced spacecraft to orbit Saturn and repeatedly fly through the plumes of Enceladus. By passing through the geysers multiple times, the spacecraft could collect samples of ice particles and vapor. Highly sensitive instruments could then analyze these samples for complex organic molecules, amino acids, or other potential biosignatures. Another proposal involves landing a probe near the south pole of Enceladus. This lander could analyze freshly fallen plume particles on the surface, searching for chemical patterns that might indicate biological activity. Some of the most ambitious ideas involve sending robotic probes capable of melting through the ice shell and reaching the subsurface ocean directly. Such missions would be extremely challenging. The ice crust of Enceladus may be several kilometers thick in some areas, and drilling or melting through it would require advanced technology and enormous amounts of energy. However, because the plumes already carry ocean material into space, scientists may not need to penetrate the ice at all. The moon itself is already delivering samples from its ocean directly into space. This makes Enceladus one of the most accessible ocean worlds in the solar system. Several space agencies, including NASA and the European Space Agency, are currently studying mission concepts that could return to Enceladus in the coming decades. One of the most exciting proposals is known as the Enceladus Orbilander. This mission concept combines two spacecraft into one. First, it would orbit Saturn and conduct detailed studies of the moon's plumes from space. Later, it would descend and land on the surface near the South Pole. Once on the surface, the spacecraft could analyze freshly deposited ice from the plumes and search for organic molecules or possible biological signatures. Such a mission could provide unprecedented insight into the chemistry of Enceladus's hidden ocean. But the scientific interest in Enceladus extends beyond the search for life. Studying the moon may also help scientists understand how ocean worlds form and evolve throughout the universe. Icy moons with subsurface oceans appear to be surprisingly common. Jupiter's moon Europa likely contains a deep ocean beneath its icy crust. Saturn's moon Titan may also possess a hidden ocean beneath its thick atmosphere. Even distant dwarf planets, such as Pluto, may contain subsurface oceans trapped beneath layers of ice. If oceans can exist inside small icy worlds throughout the solar system, then similar environments may also exist around other stars. Many of the planets discovered around distant stars are believed to be icy bodies orbiting far from their suns. Some of these worlds may contain internal oceans heated by tidal forces or radioactive elements. This means that the number of potentially habitable environments in the universe may be far larger than scientists once imagined. Instead of focusing only on Earth-like planets with sunlight and atmospheres, researchers are now considering a much broader range of environments where life might exist. Hidden oceans beneath frozen surfaces, dark worlds warmed by tidal forces, subsurface ecosystems powered entirely by chemistry. Enceladus has become one of the most important examples of this new way of thinking. A tiny moon orbiting Saturn, a world that appears frozen and lifeless from the outside, yet beneath its icy crust may lie a warm ocean filled with chemical energy, and perhaps even living organisms. For now, these possibilities remain unanswered, but every plume that erupts from the South Pole carries new clues into space, offering scientists a rare opportunity to study an alien ocean without ever leaving orbit. And somewhere within that hidden ocean, beneath kilometers of ice and darkness, there may be environments that resemble the earliest ecosystems on Earth. If life truly exists beyond our planet, Enceladus may be one of the places where we find it first. One of the most fascinating aspects of Enceladus is how such a small world manages to remain active for so long. In planetary science, size usually determines whether a celestial body can maintain geological activity. Larger planets and moons retain heat for billions of years, allowing processes like volcanism, tectonics, and atmospheric circulation to continue. Smaller bodies, however, cool down quickly. Once their internal heat dissipates, they become frozen relics of the early solar system. Enceladus should have followed that pattern. With a diameter of only about 500 kilometers, the moon is far smaller than Earth's moon and dramatically smaller than major icy moons like Europa or Titan. In theory, Enceladus should have lost most of its internal heat billions of years ago, leaving it as a frozen block of ice and rock orbiting Saturn in silence. Yet the reality is very different. Enceladus is still active today. Water vapor erupts from its south pole. Heat escapes through enormous fractures. Its surface is continuously reshaped by geological processes. The question that continues to puzzle scientists is simple but profound. How does such a small world generate enough energy to sustain this activity? The primary explanation involves tidal heating, the process created by gravitational forces stretching and compressing the moon as it orbits Saturn. Every time Enceladus travels along its elliptical orbit, Saturn's gravity pulls on it with slightly different intensity. This constant variation flexes the moon's interior, generating heat through friction. But tidal heating alone may not explain the full amount of energy observed. When scientists measured the heat escaping from the South Polar region using Cassini's instruments, they discovered that the energy output was far greater than early models predicted. The tiger stripe fractures were releasing several gigawatts of heat into space, comparable to the energy output of many large power plants combined. For a small icy moon, this was extraordinary. Researchers began exploring additional mechanisms that might help explain the excess heat. One of the most important possibilities involves the structure of Enceladus's rocky core. Instead of being a solid, compact mass, the core may be highly porous, filled with fractures and cavities. If water from the subsurface ocean circulates through these pores, tidal flexing could generate enormous amounts of friction inside the rock itself. As water moves through the porous core, the mechanical stress caused by Saturn's gravity would continually grind the rock and fluid together. This process could produce large amounts of heat, warming the surrounding water and helping maintain the ocean above. This internal circulation could also explain the chemical composition of the plumes observed by Cassini. When water flows through hot rock, it dissolves minerals and chemical compounds along the way. These substances then become part of the ocean's chemistry before eventually escaping through the plumes. Cassini detected evidence of salts, carbon compounds, and silica particles within the plume material. The presence of silica was particularly important because these particles likely formed at very high temperatures, possibly near hydrothermal vents on the ocean floor. Hydrothermal vents occur when heated water rises through cracks in the crust and mixes with colder surrounding water. On Earth, these vents create rich chemical environments where life can thrive without sunlight. If similar vents exist on the ocean floor of Enceladus, they could provide both heat and nutrients for potential microbial ecosystems. Another possible heat source inside Enceladus involves chemical reactions within the rocky core itself. When water interacts with certain minerals found in ultramafic rock, a process called serpentinization can occur. This reaction produces hydrogen gas and releases energy. The hydrogen detected in Enceladus's plumes may be evidence that serpentinization is taking place inside the moon. This process is important because it can create chemical energy that living organisms might use for metabolism. On Earth, microorganisms near hydrothermal vents often rely on reactions involving hydrogen and carbon dioxide to produce energy. These reactions form methane and other organic compounds that support complex ecosystems in the deep ocean. If similar chemical environments exist inside Enceladus, they could potentially support microbial life. But even without life, these reactions help explain how the moon maintains its internal heat and chemical complexity. Another intriguing aspect of Enceladus's activity involves the thickness of its icy crust. Measurements suggest that the ice shell covering the moon's ocean is not uniform. In some areas, the crust may be more than 30 kilometers thick, while in others, it could be significantly thinner. Near the South Pole, where the tiger stripe fractures are located, the crust appears to be much thinner than elsewhere. This thinning may allow heat from the interior to escape more easily in that region. As heat rises, it weakens the ice above, making it easier for fractures to form and widen. Once cracks appear, they allow warm water from the ocean to rise closer to the surface. This water may partially freeze as it ascends, creating slushy mixtures of ice and liquid that move through the fractures. When this material reaches the vacuum of space, the sudden drop in pressure causes it to expand rapidly and erupt outward as geysers. The cycle then repeats. Tidal forces flex the moon's crust, widening the fractures. Ocean water rises through the cracks. Pressure builds beneath the surface. Eventually, the water bursts outward into space, carrying tiny particles of the ocean with it. This constant process helps maintain the open fractures and prevents them from freezing shut. Over time, the plumes also play an important role in shaping the surface of Enceladus itself. When the geysers erupt, not all of the material escapes the moon's gravity. Many particles fall back down onto the surface as fine ice crystals. This continuous snowfall gradually covers the surrounding terrain with fresh ice. This process explains why Enceladus appears so bright when viewed from space. The moon's surface reflects almost all of the sunlight that reaches it. Its reflectivity, or albedo, is close to 1.0, meaning it reflects nearly 100% of incoming light. This makes Enceladus the most reflective known object in the solar system. But the fresh ice deposited by the plumes does more than brighten the surface. It also slowly reshapes the landscape. Over time, the accumulation of plume material can bury older terrain and smooth out impact craters. This creates large regions of relatively young surface, where geological features appear fresh and well preserved. This resurfacing process is one of the reasons scientists know that Enceladus has remained active for long periods of time. If the moon had stopped erupting millions or billions of years ago, its surface would likely be covered in ancient impact craters like many other icy moons. Instead, much of the South Polar region looks remarkably young. Another fascinating discovery involves how the plumes interact with Saturn's magnetic field. As particles from the geysers escape into space, they become ionized by radiation and solar energy. These charged particles are then influenced by Saturn's powerful magnetosphere. The result is a complex environment of plasma and electromagnetic interactions surrounding the moon. Cassini detected strong disturbances in Saturn's magnetic field when passing near Enceladus, confirming that large amounts of ionized material were being released. Some of these particles eventually become trapped within Saturn's magnetosphere, contributing to a large torus of plasma around the planet. Others drift outward to replenish Saturn's E-ring, forming a vast halo of ice particles extending far beyond the orbit of Enceladus. This means that the moon's activity is not limited to its own surface. It is actively shaping the environment around Saturn itself. In many ways, Enceladus functions almost like a miniature planetary engine, continuously pumping material into the surrounding space. But despite everything scientists have learned, many questions remain unanswered. How long has Enceladus been active? Is the subsurface ocean stable over billions of years? Or is it a relatively recent development? Could the ocean contain complex organic chemistry or even living organisms? And perhaps most intriguingly, how many other icy worlds throughout the universe might host similar hidden oceans beneath frozen surfaces? These questions continue to drive scientific interest in Enceladus. What was once considered a small, insignificant moon has now become one of the most important objects in planetary science. A frozen world orbiting Saturn, a moon that should have been silent and lifeless long ago. Yet somehow it continues to erupt into space, revealing glimpses of a hidden ocean beneath its icy shell. For much of human history, the search for life beyond Earth focused on planets that looked similar to our own world. Scientists imagined that alien life would most likely be found on warm planets orbiting within the habitable zone of their stars, places where liquid water could exist on the surface under sunlight. But discoveries in the last few decades have dramatically changed that perspective. Instead of searching only for Earth-like planets, scientists are now considering the possibility that life might exist in environments very different from our own. Hidden oceans beneath thick layers of ice may actually be among the most promising places to look. Enceladus has become one of the strongest examples of this new idea. Unlike Earth, the ocean of Enceladus is not exposed to sunlight. It lies buried beneath a thick shell of ice that isolates it completely from the surface. The moon receives very little energy from the distant sun, and the surface temperature remains incredibly cold. Yet beneath that frozen exterior, conditions may be surprisingly dynamic. The key factor that keeps Enceladus active is its relationship with Saturn. The giant planet's immense gravity constantly pulls and stretches the moon as it travels along its orbit. This tidal flexing generates heat inside the moon, preventing the ocean from freezing completely. In effect, Enceladus is heated from within rather than from above. This process may create a stable internal environment that has existed for millions or possibly even billions of years. If the ocean has been present for such long periods of time, it could provide enough stability for complex chemical processes to develop. Given sufficient time and the right conditions, these processes might even lead to the emergence of life. But what would life on Enceladus actually look like? Scientists believe that if organisms exist there, they would most likely be microscopic, similar to the simplest forms of life found on Earth. These organisms would probably live in the dark ocean beneath the ice, possibly clustered around hydrothermal vents on the seafloor. On Earth, hydrothermal vents support entire ecosystems that survive without sunlight. Instead of photosynthesis, these organisms rely on chemical reactions involving hydrogen, methane, and other compounds. The energy produced by these reactions allows microorganisms to grow and reproduce even in complete darkness. If similar vents exist inside Enceladus, they could provide both heat and chemical energy to support microbial life. One of the most important discoveries made by the Cassini spacecraft was the detection of molecular hydrogen in the plumes erupting from the moon. Hydrogen is a key ingredient in many chemical reactions that can support microbial metabolism. Its presence suggests that chemical reactions between water and rock are occurring deep inside the moon. Another crucial ingredient for life is organic chemistry. Cassini detected several simple organic molecules within the plume material. These compounds contain carbon, hydrogen, oxygen, and nitrogen, elements that form the basic framework of biological molecules. More recently, scientists analyzing Cassini data discovered evidence of larger and more complex organic compounds within the plumes. Some of these molecules appear to be relatively heavy and structurally complex, suggesting that they formed in a chemically rich environment. While these molecules are not proof of life, they demonstrate that the ocean of Enceladus contains active organic chemistry. This discovery significantly increased interest in the Moon as a potential habitat. Another factor that makes Enceladus particularly attractive for exploration is the accessibility of its ocean material. On most ocean worlds, the subsurface ocean is completely sealed beneath kilometers of ice. Reaching it would require drilling through the crust, which would be extremely difficult with current technology. Enceladus, however, is different. The Moon is already ejecting ocean material into space. The geysers erupting from the tiger stripes send water vapor, ice particles, and dissolved chemicals hundreds of kilometers above the surface. This means that spacecraft can sample the contents of the ocean simply by flying through the plumes. Cassini performed several such flybys during its mission, collecting valuable data about the composition of the material escaping from the Moon. Future missions could perform much more detailed analyses. A spacecraft equipped with advanced instruments could measure the chemical composition of the plumes with far greater precision. It could search for amino acids, lipids, or other complex molecules that might indicate biological activity. It could even attempt to detect patterns in the chemistry that suggest metabolic processes. Some scientists have proposed missions that would fly repeatedly through the plumes at different altitudes and locations. By comparing the composition of particles in different jets, researchers might be able to map the chemistry of the ocean beneath the surface. Other mission concepts involve landing on the surface near the South Pole. A lander placed in this region could analyze freshly fallen plume particles that settle on the surface like snow. Because these particles originate from the subsurface ocean, they may contain valuable chemical clues. One of the most ambitious mission ideas involves sending a probe capable of descending into the ocean itself. Such a probe would likely need to melt its way through the ice shell using a specialized device sometimes called a cryobot. Once it reached the ocean, it could release a small autonomous submarine to explore the underwater environment. Although such missions remain far in the future, they represent the kind of exploration that could finally answer the question of whether life exists on Enceladus. The technological challenges would be enormous, but the scientific rewards could be even greater. Discovering life beyond Earth would fundamentally change humanity's understanding of biology and the universe. It would demonstrate that life is not unique to our planet. It would suggest that wherever the right conditions exist, liquid water, chemical nutrients, and energy, life may find a way to emerge. Even if Enceladus does not contain living organisms, studying its ocean could still reveal important information about how habitable environments form in icy worlds. Understanding the chemistry and dynamics of Enceladus could help scientists learn more about other ocean moons such as Europa, Ganymede, and Titan. It could also help researchers identify similar environments on planets orbiting distant stars. Over the past decade, astronomers have discovered thousands of exoplanets, worlds orbiting other stars throughout the galaxy. Many of these planets appear to be icy bodies located far from their host stars. Some of them may experience tidal heating similar to Enceladus, potentially creating hidden oceans beneath their surfaces. If that is the case, then the number of possible habitats for life in the universe could be far larger than previously imagined. Instead of searching only for Earth-like planets, scientists may need to consider a wide range of ocean worlds hidden beneath frozen shells. Enceladus may represent just one example of a much larger population of habitable environments scattered throughout the galaxy. And yet, despite all of this scientific interest, Enceladus remains a tiny moon orbiting quietly around Saturn. From a distance, it appears small and unremarkable, just another icy satellite lost among dozens of others in the Saturn system. But beneath its brilliant surface lies an active ocean that continues to erupt into space, a hidden sea that may contain chemical reactions similar to those that once gave rise to life on Earth. And somewhere within that dark ocean, beneath kilometers of ice and the faint light of a distant sun, there may exist environments where life could survive in ways we are only beginning to imagine. Enceladus does not exist in isolation. It is part of a vast and complex planetary system dominated by Saturn, a giant world surrounded by rings and dozens of moons. Within this environment, Enceladus interacts constantly with Saturn's gravity, magnetic field, and surrounding particles. These interactions shape not only the moon itself, but also the space around it. To truly understand Enceladus, scientists must also understand how it fits into the broader Saturn system. Saturn is the second largest planet in the solar system, with a mass more than 95 times greater than Earth's. Its gravitational pull dominates everything nearby, controlling the motion of its moons and shaping the structure of its famous ring system. Enceladus orbits Saturn at a distance of about 238,000 kilometers from the planet's cloud tops. At this distance, the moon completes one orbit roughly every 33 hours. This means that Enceladus experiences Saturn's gravitational influence continuously, every moment of its existence. But Saturn is not the only body influencing the moon. Several of Saturn's other moons also interact gravitationally with Enceladus. One of the most important of these is the moon Dione. Dione is larger than Enceladus and orbits Saturn slightly farther away. The two moons are locked in a precise orbital resonance. For every two orbits, Enceladus completes around Saturn. Dione completes exactly one. This gravitational relationship might seem minor, but it plays a crucial role in maintaining Enceladus's geological activity. Orbital resonances prevent Enceladus from settling into a perfectly circular orbit. Instead, the moon's path around Saturn remains slightly elliptical. As a result, the distance between Enceladus and Saturn constantly changes during each orbit. When the moon moves closer to Saturn, the planet's gravity pulls more strongly on it. When the moon moves farther away, that gravitational pull weakens slightly. This constant variation in gravitational force causes Enceladus to flex repeatedly. The moon is literally stretched and squeezed as it travels through space. Inside the moon, this flexing generates friction within the ice shell and the rocky core. Over time, that friction produces heat. This tidal heating is one of the key reasons Enceladus remains active today. Without the gravitational influence of Saturn and the orbital resonance with Dione, the Moon would likely have cooled and frozen billions of years ago. Instead, these gravitational forces act like an engine that keeps Enceladus alive. The effects of Enceladus extend far beyond the Moon itself. As the plumes erupt from the South Pole, enormous quantities of water vapor and ice particles are injected into space. Some of these particles fall back onto the surface of the Moon, but many escape its weak gravity entirely. These particles spread outward and become part of Saturn's E-ring. Saturn's E-ring is the largest and most diffuse ring in the Saturn system, unlike the bright rings closer to the planet, which consist of large chunks of ice. The E-ring is made mostly of microscopic particles. This ring extends hundreds of thousands of kilometers across space and is centered roughly around the orbit of Enceladus. Scientists now believe that Enceladus is the primary source of the E-ring. Every second, the Moon ejects hundreds of kilograms of material into space through its geysers. Over time, this continuous flow replenishes the particles that make up the ring. Without Enceladus, the E-ring would slowly fade away as its particles drift outward or fall towards Saturn. In this sense, the Moon is not just another satellite orbiting Saturn. It is actively feeding one of the planets, despite everything scientists have learned about Enceladus. One of the most remarkable aspects of this Moon is how recently its secrets were discovered. For most of human history, Enceladus was simply a distant point of light orbiting Saturn. Even after spacecraft first visited the Saturn system, the true nature of this Moon remained hidden. The turning point came with the arrival of the Cassini-Huygens mission, one of the most ambitious planetary exploration projects ever launched. Cassini was the result of a collaboration between NASA, the European Space Agency, and the Italian Space Agency. The spacecraft was launched in October 1997 and began a long journey through the solar system that would last nearly 7 years before reaching Saturn. After traveling billions of kilometers, Cassini finally entered orbit around Saturn in July 2004. Its mission was to study the planet, its rings, and its moons in unprecedented detail. At the time, most scientists expected the mission's most exciting discoveries to come from Titan, Saturn's largest moon. Titan has a thick atmosphere and vast lakes of liquid methane, making it one of the most Earth-like environments beyond our planet. But soon after Cassini began observing the Saturn system, a much smaller moon started drawing unexpected attention. That moon was Enceladus. Early images taken by Cassini revealed a surface that appeared unusually smooth and bright. Large portions of the moon showed very few impact craters, suggesting that geological activity had resurfaced the terrain relatively recently. For a moon of Enceladus' size, this was already surprising. But the real shock came when Cassini's instruments detected something unusual near the South Pole. There appeared to be a faint cloud of particles surrounding the moon. At first, scientists were unsure what they were seeing. The particles could have been debris from micrometeorite impacts or material trapped in orbit around the moon. But as Cassini continued its observations, the data began pointing towards something far more extraordinary. The cloud appeared to originate from specific regions near the South Pole, and those regions seemed to be actively releasing material into space. In 2005, Cassini performed several close flybys of Enceladus, passing only a few hundred kilometers above the surface. During these encounters, the spacecraft's cameras captured the first direct images of enormous plumes erupting from the moon's south polar fractures. The discovery stunned the scientific community. No one expected a moon this small to produce such dramatic activity. The plumes appeared as massive curtains of vapor and ice particles shooting hundreds of kilometers into space. Some jets were narrow and concentrated, while others formed broad clouds that spread outward above the surface. Cassini's instruments soon confirmed that these plumes consisted primarily of water vapor and tiny ice grains. This was the first clear evidence that Enceladus might contain liquid water beneath its surface. But the surprises did not stop there. During one daring maneuver, Cassini flew directly through one of the plumes. As the spacecraft passed through the cloud of particles, its instruments analyzed the composition of the material. The results revealed far more than simple water ice. The plumes also contained organic molecules, carbon dioxide, methane, ammonia, and various salts. These compounds strongly suggested that the material was coming from an underground ocean interacting with rocky material below. Even more astonishing was the discovery of molecular hydrogen. Hydrogen gas is often produced when water reacts with hot rock in hydrothermal systems. On Earth, such environments exist at the ocean floor near hydrothermal vents. These vents are among the most biologically productive ecosystems on our planet. The detection of hydrogen on Enceladus indicated that similar reactions might be taking place deep inside the moon. In other words, the ocean beneath Enceladus might not simply be a cold body of water trapped beneath ice. It could be a chemically active environment, possibly containing hydrothermal vents capable of supporting microbial life. This discovery instantly transformed Enceladus into one of the most important targets in the search for extraterrestrial life. Over the next decade, Cassini continued studying the moon during multiple flybys. Each new encounter provided more data about the plumes, the surface, and the interior structure of the moon. The spacecraft mapped the tiger stripe fractures in greater detail and measured the temperature of the surrounding terrain. It also analyzed the particles within Saturn's E-ring, confirming that the ring is largely composed of material originating from Enceladus. By the end of the mission, Cassini had completely rewritten our understanding of this small moon. What was once thought to be a frozen, inactive world turned out to be one of the most dynamic environments in the outer solar system. A moon with an active ocean. A moon with geysers erupting into space. A moon with the chemical ingredients necessary for life. In September 2017, the Cassini mission came to an end in one of the most dramatic finales in space exploration history. After more than 13 years orbiting Saturn, the spacecraft was deliberately sent into the planet's atmosphere. This maneuver, known as the Grand Finale, ensured that Cassini would not accidentally contaminate potentially habitable moons like Enceladus or Titan with microbes from Earth. As the spacecraft plunged into Saturn's atmosphere, it transmitted data until the final moments before it was destroyed by the planet's intense heat and pressure. By that time, Cassini had revolutionized our understanding of the Saturn system, but perhaps its greatest legacy was revealing the hidden ocean world of Enceladus. Today, scientists continue to analyze the enormous amount of data collected by the spacecraft. Even years after the mission ended, new discoveries are still emerging from the Cassini archive. For example, recent analyses have revealed that the organic molecules within the plumes may be larger and more complex than originally thought. Some of these compounds could contain structures similar to those found in biological chemistry. These findings continue to strengthen the case for future missions to Enceladus. Several space agencies are currently studying mission proposals designed specifically to return to this moon. Some missions would focus on flying repeatedly through the plumes to analyze their chemistry in even greater detail. Others might attempt to land near the South Pole and study freshly fallen plume material on the surface. Each new mission concept aims to answer the same fundamental question: could life exist in the ocean of Enceladus? For now, the moon continues its silent orbit around Saturn, releasing enormous geysers of water vapor into space. Every eruption carries fragments of its hidden ocean outward into the darkness. Tiny clues waiting to be studied by future explorers. And somewhere beneath its frozen surface, kilometers below the bright icy crust, an alien ocean continues to flow in the darkness, an ocean that may hold answers to one of the greatest questions humanity has ever asked. The discovery of Enceladus changed more than just our understanding of Saturn's moons. It fundamentally reshaped how scientists think about the habitability of the solar system. Before Cassini revealed the hidden ocean beneath its icy crust, most researchers believed that environments capable of supporting life had to exist on planetary surfaces exposed to sunlight. Enceladus proved that assumption might be wrong. Life does not necessarily require warmth from a nearby star. It may survive in completely dark environments, powered only by internal heat and chemical reactions deep beneath the surface of icy worlds. This realization has led scientists to a new concept often referred to as ocean worlds. Ocean worlds are celestial bodies that contain large amounts of liquid water beneath their surfaces. In many cases, this water is hidden beneath thick shells of ice, protected from the harsh conditions of space. Enceladus is now considered one of the most compelling ocean worlds in the solar system, but it is not the only one. Jupiter's moon Europa is perhaps the most famous example. Europa has long been suspected to contain a vast ocean beneath its frozen surface. The moon's cracked ice shell suggests that warm water may lie below, constantly reshaping the terrain. Another candidate is Ganymede, the largest moon in the solar system. Beneath its icy crust may lie several layers of subsurface oceans stacked between different layers of ice. Saturn's largest moon, Titan, may also contain a hidden ocean beneath its thick atmosphere and surface lakes of methane. Even distant dwarf planets like Pluto may possess subsurface oceans trapped beneath their icy shells. The more scientists study the outer solar system, the more they realize that oceans beneath ice may be surprisingly common. This discovery has enormous implications for the search for life. If liquid water can exist inside small icy worlds far from the sun, then similar environments might also exist around planets orbiting distant stars. Some astronomers now believe that subsurface ocean worlds could be one of the most common types of habitable environments in the galaxy. In these environments, life would not depend on sunlight. Instead, it would rely on internal heat sources such as tidal heating or radioactive decay. Chemical reactions between water and rock could provide the energy necessary to support microbial ecosystems. Enceladus represents one of the clearest examples of how such environments might work. The Moon's internal heat is generated primarily by tidal forces from Saturn. As the Moon moves along its orbit, Saturn's gravity continuously stretches and compresses the interior. This process generates friction and heat, preventing the ocean from freezing solid. This heat also drives the geological activity that creates the plumes erupting from the South Pole. But the existence of Enceladus raises another intriguing question. Could there be other ocean worlds that are even more active than Enceladus? Some researchers believe that certain icy moons may contain oceans that are far deeper than anything found on Earth. Europa's ocean, for example, may be more than 100 kilometers deep, far deeper than Earth's deepest ocean trenches. If hydrothermal vents exist on the seafloor of such oceans, they could create enormous environments where life might flourish. But exploring these oceans presents enormous technological challenges. Unlike Enceladus, most ocean worlds do not naturally eject their internal water into space. Their oceans remain completely sealed beneath thick ice shells. Reaching them would require spacecraft capable of drilling or melting through kilometers of ice. Such missions are currently beyond the capabilities of existing technology, though scientists are actively studying how they might be accomplished in the future. One possible solution involves the use of cryobots, robotic probes designed to melt their way downward through ice. A cryobot would carry a heat source capable of slowly melting the ice beneath it. As it descended, it could release communication cables behind it to maintain contact with the surface. Once the probe reached the ocean, it could deploy a small autonomous submarine to explore the underwater environment. Such missions would be extremely complex and expensive, but they could provide direct access to some of the most intriguing environments in the solar system. Enceladus offers a unique advantage compared to these other worlds. Because the Moon is already ejecting ocean material through its plumes, spacecraft can study the contents of the ocean without needing to penetrate the ice. This makes Enceladus one of the easiest ocean worlds to investigate. Future missions could carry advanced mass spectrometers capable of detecting extremely small traces of organic compounds. These instruments could search for amino acids, lipids, or other molecules associated with biological processes. They might even detect subtle patterns in the chemistry that suggest metabolic activity. Another possibility involves searching for microscopic particles that resemble cells or fragments of biological material. If organisms exist within the ocean, some of their remains might be carried upward through the plumes and frozen into the ice particles that escape into space. By analyzing these particles, scientists could potentially identify evidence of life. Even if no life is found, studying the chemistry of Enceladus could still provide valuable insights into how life begins. One of the biggest mysteries in science is how life first emerged from non-living chemistry. On Earth, this process occurred billions of years ago, and much of the evidence has been lost over time. But environments like Enceladus may preserve chemical conditions similar to those that existed on the early Earth. If researchers can study these environments in detail, they might learn more about the steps that lead from simple organic molecules to complex living systems. Another important aspect of Enceladus is the possibility that its ocean may be relatively young. Some models suggest that the ocean could have formed relatively recently in geological terms, perhaps within the last few 100 million years. If this is true, it raises fascinating questions about how quickly life could emerge in a new ocean environment. On Earth, life appears to have developed relatively quickly after the planet's oceans formed. If life can emerge rapidly under the right conditions, then it may not be uncommon in environments like Enceladus. Of course, it is also possible that the ocean contains no life at all. Even so, studying Enceladus would still provide critical insights into the limits of habitability in the universe. By understanding why life does or does not exist there, scientists can refine their search for habitable worlds elsewhere. The importance of Enceladus extends far beyond the Saturn system. It serves as a natural laboratory for studying how oceans can exist in places once thought too cold and distant to support liquid water. It challenges traditional assumptions about where life might exist, and it reminds us that even the smallest and most overlooked worlds can hold extraordinary surprises. A moon only 500 kilometers wide, a frozen world orbiting nearly 1 billion kilometers from the Sun. Yet beneath its icy crust lies an ocean that continues to erupt into space, revealing glimpses of an alien environment hidden deep within the darkness of the outer solar system. The more scientists studied Enceladus, the more it became clear that this small moon is not simply an isolated curiosity within the Saturn system. Instead, it may represent an entirely new category of worlds, places where oceans exist beneath frozen surfaces and remain active for immense spans of time. These worlds challenge traditional ideas about planetary evolution and raise profound questions about how many similar environments might exist across the universe. For decades, the search for life beyond Earth focused on planets that orbit within the habitable zone of their stars. This region, sometimes called the Goldilocks zone, is where temperatures allow liquid water to exist on a planet's surface. Earth lies comfortably within this zone around the Sun, which is one reason life was able to develop here. But Enceladus demonstrates that surface conditions may not be the only factor that matters. Even though the moon orbits far beyond the traditional habitable zone, it still contains a liquid ocean. That ocean exists because internal heating keeps the water from freezing solid. The energy comes not from sunlight, but from gravitational forces and chemical reactions within the moon's interior. This realization dramatically expands the number of possible environments where life might exist. Instead of searching only for Earth-like planets, scientists now recognize that icy moons with subsurface oceans may also be capable of supporting life. In fact, some researchers believe that these hidden oceans may be among the most common habitats in the universe. Within our own solar system, several moons are now believed to contain internal oceans. Europa, one of Jupiter's largest moons, likely hides a vast ocean beneath its icy crust. The moon's surface is covered with fractures and ridges that suggest the ice is floating on liquid water below. Tidal heating generated by Jupiter's immense gravity may keep that ocean warm enough to remain liquid. Another example is Ganymede, the largest moon in the solar system. Beneath its thick ice shell may lie several layers of ocean, trapped between different types of ice. Callisto, another moon of Jupiter, may also contain a subsurface ocean, although it appears to be less active than Europa. Titan, Saturn's largest moon, is perhaps the most complex of all. Its surface contains lakes and rivers of liquid methane and ethane. While deep beneath the crust, scientists believe there may be an enormous water ocean. Even the distant dwarf planet Pluto shows evidence that a subsurface ocean may once have existed beneath its icy crust. These discoveries suggest that the solar system may contain far more liquid water than scientists once believed. In fact, when all of these hidden oceans are added together, the total volume of water may exceed the amount found in Earth's oceans many times over. This raises an extraordinary possibility. If liquid water environments exist beneath the ice of many moons, then the conditions necessary for life may be widespread throughout the solar system. Enceladus stands out among these worlds because of one crucial feature. It is actively releasing material from its ocean into space. This means scientists do not need to drill through kilometers of ice to study its interior. Instead, the moon itself provides samples of its ocean through the plumes erupting from the South Pole. Every plume carries tiny ice particles and vapor that originated from the ocean below. These particles contain chemical clues about the environment within the moon. When Cassini flew through the plumes, its instruments detected water, organic molecules, salts, and molecular hydrogen. These ingredients strongly suggest that the ocean contains the basic components required for life. But the Cassini mission also revealed something else that surprised scientists. The plumes of Enceladus appeared to be incredibly dynamic. Some jets are stronger than others, and their intensity changes depending on the moon's position in its orbit around Saturn. When Enceladus moves farther from the planet, the fractures at the South Pole widen slightly, allowing more material to escape. When the moon moves closer to Saturn, the fractures compress and the eruptions become weaker. This rhythmic pattern indicates that the moon's activity is directly controlled by tidal forces. In effect, Enceladus is constantly flexing under Saturn's gravitational pull. This flexing not only generates heat, but also helps maintain the fractures through which the plumes erupt. Another intriguing aspect of Enceladus is how its internal ocean may circulate. Some scientists believe that the ocean may experience slow currents driven by differences in temperature and salinity. Warmer water rising from hydrothermal vents at the seafloor could gradually move upward toward the ice shell before cooling and sinking again. These circulation patterns could distribute nutrients and chemical compounds throughout the ocean. On Earth, similar processes occur in our oceans, where currents help move heat and nutrients around the planet. If such circulation exists within Enceladus, it could create a complex and dynamic environment beneath the ice. The ocean might not be a quiet, stagnant body of water. Instead, it could be an active system with currents, chemical gradients, and varying temperatures. Such conditions could provide many potential niches where microorganisms might survive. Another mystery scientists are trying to understand involves the age of Enceladus's ocean. Some models suggest that the ocean may have existed for billions of years, possibly since the early formation of the Saturn system. Other models propose that the ocean may be much younger, perhaps forming only hundreds of millions of years ago due to changes in the Moon's orbit and internal heating. If the ocean is ancient, it may have had enough time for complex chemistry and possibly life to develop. If it is relatively young, then scientists may be observing a world in the early stages of ocean formation. Determining the age of the ocean is difficult because most of the evidence lies beneath the ice shell, hidden from direct observation. However, the study of plume chemistry may eventually provide clues about how long the ocean has existed. Another question involves the thickness of the ice shell covering the ocean. Current estimates suggest that the ice crust may be roughly 20 to 30 kilometers thick in most areas. Near the South Pole, however, the crust may be significantly thinner. In some regions around the tiger stripe fractures, the ice may be only a few kilometers thick. This thinner crust may explain why the plumes are concentrated in that region. Heat from the interior can escape more easily through thin ice, allowing fractures to form and remain open. These fractures act as natural conduits connecting the ocean to space. But the structure of the ice shell may also change over time. Tidal heating, plume activity, and internal convection could gradually reshape the crust. Some regions may thicken as ice refreezes, while others may thin as heat rises from below. Understanding these processes is important because they influence how material moves between the ocean and the surface. The plumes of Enceladus may represent only one part of a much larger cycle of water and ice moving through the Moon's interior. Water rising through the fractures eventually freezes as it reaches space, while some of it falls back to the surface as fine ice particles. Over time, these particles accumulate and form fresh layers of ice that cover the terrain. This constant cycle of eruption and deposition slowly reshapes the Moon's surface. It also helps explain why Enceladus remains the brightest object in the solar system. Fresh ice from the plumes continually coats the surface, reflecting nearly all the sunlight that reaches the Moon. From a distance, Enceladus appears almost pure white against the darkness of space. Yet beneath that brilliant exterior lies one of the most mysterious environments known to science: a global ocean hidden beneath ice, an ocean that may contain hydrothermal vents, chemical reactions, and possibly even microbial ecosystems. A small moon orbiting Saturn, quietly releasing fragments of its hidden ocean into the void. Each plume carries another clue about the strange and fascinating world beneath the surface. A world that may hold answers to questions scientists have been asking for generations. Questions about how oceans form, how chemical environments evolve, and whether life might exist far beyond the boundaries of Earth. For most of human history, the idea that life might exist beyond Earth belonged more to imagination than science. Ancient philosophers speculated about worlds beyond our own, but without the tools to explore space, these ideas remained purely theoretical. Even after the invention of telescopes, the distant planets and moons of the solar system appeared as little more than small points of light. It was only in the last few decades that humanity began to understand how complex and diverse these worlds truly are. Among all the discoveries made during the modern era of planetary exploration, few have been as surprising as Enceladus. At first glance, Enceladus seems insignificant. It is small, only about 500 kilometers across, and it orbits far from the warmth of the sun. Its surface is covered in ice, and for centuries it appeared to be nothing more than another frozen moon circling Saturn. But beneath that quiet appearance lies one of the most extraordinary environments in the solar system, a hidden ocean, an ocean that is not frozen solid despite the extreme cold of space, an ocean that interacts with a rocky seafloor where chemical reactions may produce heat and energy, and most astonishing of all, an ocean that is actively erupting into space. The discovery of the plumes rising from Enceladus completely changed how scientists view icy worlds. These geysers reveal that the moon is not geologically dead, but surprisingly active. The fractures near the South Pole act like enormous vents, releasing water vapor and ice particles hundreds of kilometers above the surface. Each plume is a window into the hidden ocean beneath the ice. When the Cassini spacecraft flew through these plumes, it detected water, salts, organic molecules, and hydrogen gas. Together, these ingredients form a chemical environment that closely resembles conditions found near hydrothermal vents on Earth. On our planet, hydrothermal vents support ecosystems that survive without sunlight. Microorganisms living in these environments use chemical reactions instead of photosynthesis to produce energy. The possibility that similar environments might exist on Enceladus is one of the most exciting discoveries in planetary science. If hydrothermal vents exist on the ocean floor beneath the moon's icy crust, they could provide the heat and nutrients necessary to support microbial life. Of course, the presence of these ingredients does not prove that life exists there, but it shows that Enceladus possesses many of the conditions that scientists believe are necessary for life to emerge: liquid water, chemical nutrients, sources of energy. For decades, Mars was considered the most promising place to search for life beyond Earth. While Mars once had rivers and lakes billions of years ago, most of its water has long since disappeared. Enceladus presents a very different situation. Its ocean appears to exist today, and unlike Mars, Enceladus is actively ejecting material from that ocean into space. This unique characteristic makes the moon one of the most accessible ocean worlds for scientific study. Future spacecraft could simply fly through the plumes and collect samples of ocean material without needing to land or drill through kilometers of ice. Scientists are already designing mission concepts that could return to Enceladus in the coming decades. Some of these missions would involve orbiters capable of making repeated flybys through the plumes. By analyzing the chemistry of the particles in extreme detail, these spacecraft could search for complex organic molecules or other signs of biological activity. Other missions might attempt to land near the South Polar region. A lander could analyze freshly fallen plume particles that settle onto the surface like snow. Because these particles originate from the ocean, they may contain valuable chemical information about the environment beneath the ice. One of the most ambitious proposals involves sending a spacecraft capable of both orbiting and landing on the moon. This mission concept, sometimes referred to as an orbilander, would first study the plumes from orbit and later descend to the surface to conduct detailed analyses. Such missions could dramatically improve our understanding of the Moon's ocean and its potential habitability. The technological challenges of exploring Enceladus are significant, but the potential rewards are enormous. Finding evidence of life beyond Earth would be one of the greatest scientific discoveries in human history. It would demonstrate that life is not unique to our planet. It would show that biology can emerge in environments very different from those found on Earth, and it would suggest that living worlds may exist throughout the universe. Even if no life is discovered, studying Enceladus will still provide invaluable insights into how ocean worlds function. The Moon offers a natural laboratory for studying the chemistry and physics of icy oceans, hydrothermal systems, and a planetary evolution. It helps scientists understand how internal heating can sustain liquid water beneath frozen surfaces, and it reveals how small worlds can remain active for far longer than previously believed. Perhaps most importantly, Enceladus reminds us that the solar system still contains many mysteries waiting to be explored. For centuries, this small moon orbited Saturn unnoticed, hiding its secrets beneath a shell of ice. Only recently have we begun to glimpse the extraordinary environment beneath its surface. A world where water erupts into space. A world where chemical reactions may fuel hidden ecosystems in the darkness. A world that may hold clues about how life begins and where it might exist beyond Earth. Somewhere beneath kilometers of ice, far from the warmth of the sun, an alien ocean continues to move slowly in the darkness. Its waters circulate through fractures and vents, carrying heat and chemicals upward toward the surface. Occasionally, that hidden ocean reveals itself through towering plumes that burst into space, sending tiny fragments of its mysterious interior outward into the cosmos. Those fragments may one day help answer one of humanity's oldest questions. Are we alone in the universe? Enceladus may be small, but it has already shown us that the universe is far more complex and surprising than we once imagined. And somewhere within the frozen moons orbiting distant planets, there may be countless other oceans waiting to be discovered, each one holding the potential for new forms of life beyond our world.